University, Indonesia, for giving this opportunity for this wonderful international visiting lecture. And also, I would like to thank Ms. Novita. So now the session will be handed over to Mrs. Nafeeza. Yes, take over this session. Thank you.
Yeah, okay, sir. Ma'am, am I audible, ma'am?
Yes, ma'am.
Yeah, okay, ma'am.
Hey, welcome. Good morning, ladies and gentlemen. Welcome to the international visiting lecture today with, I'm sorry, with Miss Nafeeza as an assistant professor electrical and electronic engineering. And for the topic today is digital system. And for today's session is being live streamed on the Universitas Tekom YouTube channel. And for Miss Nafeeza, you can start the session today. Thank you.
Okay, ma'am. Okay, my hearty welcome to one and all. So today we are going to discuss about digital systems. So first of all, we are moving towards the digital system. So before that, we are having analog signals, which is a continuous signal. So we are prone to more noise, right? So for that only we are moving towards our digital system, and also in the analog signal we can't able to save, right? So for that only we are moving towards this digital system. We know that the digital system consists of only binary numbers, which is zeros and ones. Okay, so while using this digital system, it is very less prone to error compared to our analog systems. So in the digital systems, we widely used in computers, communication, automation, and control systems. So we are having more advantage than that analog signal. That's why we are moving towards this digital system. So some of the advantages I have listed here. So first is high accuracy. Why? Because so it is less affected by noise and distortion. So compared to our analog signal in the digital systems, we are having high accuracy and also easy data storage. So it can be stored and also retrieved easily. So, and third one is programmability. We can easily modify it with the help of software and with the help of more languages we are also available today. So in digital systems, for example, Verilog, VHDL, so in FPGA, we can able to easily modify it with the help of software. And next is reliability. So compared to our analog system, we have more consistent performance in digital systems. And next one is compact and it is cost effective also. With the help of this integrated circuit technology, we are having these devices as small as, so and also it is very cheaper for our usage. So the next one is easy transmission. So we can able to communicate this and travel this digital system for over a long distance without any loss, and loss is very less. So compared to our analog system, this digital system is transmitted over a long distance without any loss. So and one of the major advantage of this digital system is high speed. So it is very speed. So we are having so many logics which in this digital system, we are having so many high-speed logics which will improve our performance further. So the next is the very basic for this digital system is number system. So here it is a way of representing numbers using symbols or digits. It defines how we count, represent, and performs operations like addition, subtraction, on that numbers. So in this, it is mainly particularly worked on binary numbers. Binary numbers is nothing, it is a zeros and ones. So we are having types of number systems. Here we are having binary number, octal number, decimal number, hexadecimal number. So the binary numbers, we are having radix as 2. So we are having formula which is or minus 1. So this is a formula to calculate the number of digits. So in this binary, we are using the radix as 2. So which is 2 minus 1 is 1. So here, so we are having the numbers, always your digitals will start from the number 0. So in the binary, we are having two numbers. It is from 0 to 1. So which is 0 and 1. So in the below, I have given an example as 1011 with the base of 2. And second one is octal, which the radix is 8. So which is 8 minus 1 is 7, which is from the number 0 to 7. So always the number will start from 0 in digital. So 0 to 7 totally we are having 8 numbers. So in the below I have given an example for octal numbers, which is 57 base of 8. So on third one is decimal number. The radix is 10. So we can call it as radix or base number, which is 10. So which is, it will be start from 0 to 9. So or minus 1 means 9. So from 0 to 9, we are totally having the 10 numbers. So for example, I have written the example 1, 2, 5 base of 10. So next one is hexadecimal. The base value is 16. So the formula is r minus 1. 16 minus 1 is 15. So which is from, so here in the hexadecimal, we are having separate notation. So from 0 to 9, as it is as numbers. From 10, it is from A to F. For example, 10 means I'm going to consider it as A. So 11 means I'm going to consider as B. So up to 15, so it is F. Okay. So the next is number systems. So here we are representing 4 types of number systems. So which is first one is binary representation. So binary representation, it using the two values, which is zeros and ones. So each binary digit is called a bit here. So next one is octal representation. So in this octal representation, we are having set of 3 bits. So we consider the numbers as 3 bits. Okay, so next one is decimal representation. So this is commonly used by humans, which is a base of 10. So next is hexadecimal, which base value is 16. So here the group of binary digits into set of 4 bits. So this is normally used for our memory address and memory codes. So each representation have specific applications we are using for specific applications. So likewise, this hexadecimal representation we normally use in memory addresses and machine codes. So each and everything has separate applications that we will discuss. So some of the applications of number systems I have listed here. So this data representation, normally in the computer, we use a binary form that is called digital, which is zeros and ones. So in the digital circuit design, so for example, the number systems we are used for this application, so it's carried out with the help of logic gates, flip-flops, and microprocessors, which completely works on binary number, which is digital format, zeros and ones. So next is memory addressing, which uses a hexadecimal number, which is the last one, which uses a base 16. So that is used to represent our memory location and machine codes in a compact form. So next application is programming and coding. So in the programming and coding, we use octal or hexadecimal format for this binary simplification. So next application is communication systems. In the communication systems, we are particularly using the variety of codes for transmitting the text and data effectively. So the noise will be very less. For that only we are using this application here. So next is error detection and correction techniques. So here it uses a binary numbers. So with the help of Hamming codes and other correction techniques, we can apply very efficiently this digital circuits. So last one is digital displays and counters. Here it is used in digital clocks and calculators. So next is our basics of this digital system is logic gates. It is a very, very important topic. So which is a building block for our digital circuits. It performs logical operations on one or more input signal to produce a single output signal. Normally, we know that in digital signal, it consists of two values, which is 0 and 1. So 0 means it is a low, which is called, otherwise we call it as false. 1 means it is a high value, otherwise we call it as true. So next is some of the basic gates. Here we are having the three basic gates. So in digital, we are having three basic gates, which is AND gate, OR gate, NOT gate. So this is the basic operations which performed. So first gate is AND gate. So look at the symbol. So the symbol will be look like this. Here we are having the two inputs. So normally we are having more number of inputs in AND gate. So but the output is one and only one. So we are having 4 input AND gate, 2 input AND gate. So we are having variety of circuits. So here, this AND gates here, I have used a 2 input AND gate for a better information. So the number of inputs here is A and B. The output is Y, which is one and only Y. So Y equal to A into B. It is a Boolean expression of notating this AND gate. Okay, so here I have written the truth table. So in this truth table, we are having the inputs and output relationship. So that is mentioned here. Input here, it is A and B. Output is Y. Okay, so we are having the formula to write the combinations, which is 2 power n. Okay, so in this AND gate, I have used the 2 inputs. So 2 power n means in the n, I am going to apply the number of input variables. 2 power 2 equal to 4. Totally, we are having the combinations 4. Okay, so for that only, A, B represents at 0, 0, 0, 1, 1, 0, 1, 1. So which is from 0 to and 3. So which is a 4. Okay. So 0, 0 represents 0, 0, 1 means 1, 1, 0 means 2, 1, 1 means 3. Using the weighted code 2, 1. Okay. So in this AND gate, it will performs the multiplication operation. The logic here is when both 1 means 1. Remaining all are 0 because it consists of zeros. 0 is multiplied with anything, the answer we will get as 0. So for that only in the first one, 0 into 0 means 0, 0, 1 means 0, 1, 0 means 0, 1, 1 is 1. So the next gate is OR gate. So here also I have considered the 2 inputs. So 2 power n, which means 2 square equal to 4 combinations. The inputs are A and B, the output is Y. So the OR gate will be notated in the Boolean expression format, capital Y equal to A plus B. Okay, so in this case, the same 0, 0, 0, 1, 1, 0, 1, 1, which will be represented from 0 to 3. Okay, so the OR gate logic is when one or more 1 present means you will get the output as 1. Okay, so in the first combination, we are having both zeros means 0. Okay, so in the second combination, we are having 0 and 1. Here 1 is present, for that I have notated the output as 1. And third combination is 1, 0. So here also 1 is present, again 1. So in the fourth combination, we are having 1 and 1. So which is both or 1. So 1, the output is 1. So finally, we are having 0, 1, 1 as output for this 2 input OR gate. So third one is NOT gate. So NOT gate will perform the invert operation. So if I'm passing the 0 as input means it will produce the output as 1. Okay. So if I'm passing the 1 as input means it will produce the 0 as output. So the input, if I'm passing 0, then output will be 1. So if I'm passing the input as 1, it will produce the output as 0. So this is a symbol for your NOT gate. So the symbol notation is very, very, very important in our digital system. So in the further, we are using this logic gates to build our circuits. So next, these are the basic gates, and next we are going to see our universal gates. So universal gates is nothing. So this is the basic for all the circuit. It will perform all the basic gates operation like AND, OR, and NOT operations. So NOT, it is NAND gate is nothing but NOT plus AND gate. Okay, so it is an inverse operation of your AND gate. Okay, so same thing. So there we have seen the output if if any one of the input is 0 means there we have noted as 0. But so in this NOR we have already told it is an inversion operation of your AND gate. Obviously, if both 0 means we will notate it as 1. Okay, so and then 0 1 means 1, 1 0 means 1, and 1 1 means 0. Okay, as I said, in the AND gate the logic is if both 1 means 1, remaining all are 0. Okay, so same that in the NAND gate, so here if both 1 means 0, remaining all are 1, which is opposite to your AND gate. So again, coming to here, this Boolean expression, it is just opposite. I have notated, we have notated with the help of the inversion operation, bar. Okay, so look at this expression, y equal to a into b, the bar. Okay, so this bar notate the inverse operation. So in the previous slide, we have seen in the basic gates, y equal to a into b. Okay, so look at this. So in the NAND gate, we have notated in y equal to a into b, the whole bar. Okay, so which represents the inversion operation of your AND gate. So on the next gate is NOR gate. So it is also the inverse operation of OR gate. Okay, so in the OR gate, we seen the logic, which is, so if one or more 1 present means we will notate as 1 in OR gate. But coming to your this NOR gate, it is reverse. Okay, we are going to notate it as 0. Okay, so look at this. So 0 0 means actually we notate there 0, but here it is 1. Okay, so 0 1 means 0, 1 0 means 0, 1 1 also 0. Again, so this NOR gate is inverse operation of your OR gate. Okay, so in the Boolean expression of OR gate, we notate it as capital Y equal to A plus B. But coming to your NOR gate, it is an inverse operation of OR gate. So we have used this bar to notate your NOR gate. Capital Y equal to A plus B, the whole bar. Okay, so the next gates or some important gates are XOR and XNOR gate, exclusive OR gate and exclusive NOR gate. And one more thing, so in this, look at this AND gate symbol. So it is this AND gate symbol and it is the NAND gate symbol. The main difference in the symbol is we are using the bubble to notate your invert operation. And coming to your OR gate, here we are having the OR gate symbol. So the main difference in NOR gate, we have just added a bubble in the output side. So it denotes your inverse operation of OR gate. Okay, so the major difference compared to your AND and NAND symbol is I have just added a bubble in the output of NAND gate, and also in the NOR gate compared to your OR gate, I have added a bubble in the output of your NOR gate. Okay, so next is XOR and XNOR gate. So XOR gate and XNOR gate. So this XOR gate we are using for your error detection. So or parity codes, Hamming codes. So it is a very, very important gate. So used for your error detection and correcting codes. Okay. So here also I have used the 2 inputs and 1 output. So XOR gate symbol is like OR gate, but one of the core terminal come along with your OR gate. This is a symbol. So on here also I have used the 2 inputs XOR gate. So the formula is 2 power n, which is a 4 combinations 0 0 0 1 1 0 1 1. XOR gate is a odd one detector. Whenever it detects a odd one, it will produce the output as 1. For that only we have the truth table as 0 0 means output will be 0 since it have none of 1. Okay, so the next combination is 0 1. It consists of 1 1, which is a odd number 1, so your output will be 1. So next combination also contains a odd number of 1, which is 1 0. It will also produce output 1. And the last combination 1 1, it consists of even number of ones, so the output will be 0. Simply we can say XOR gate is a odd one detector. If it detects the odd number of ones, then your output will be 1. Okay, so the next gate is XNOR gate, which is just opposite to your XOR gate. So look at this, the truth table of XNOR gate. So the output of this gate is 1 0 0 1. So look at this XOR gate here, it is 0 1 1 0, which is just opposite to your XOR gate. So XNOR gate is just opposite of your XOR gate. And look at the symbol also. In the symbol, so this XNOR gate will perform the just inverse operation of your XOR gate. So we have added a bubble in the output side. Okay, coming to your XOR gate Boolean expression, which is capital Y equal to A XOR of B. Okay, again coming to your XNOR gate expression, capital Y equal to A XOR of B, the whole bar. This bar denotes it will perform the inverse operation of your XOR gate. So then XOR gate expression is Y equal to A XOR of B. In the Boolean theorem, it will be notated as A bar B plus A B bar. So in the XNOR gate, it is a XOR of B, the whole bar, which is notated by A bar B bar plus AB. This is a general representation of this XOR gate and XNOR gate. So these are the basic gates which we need to know before going to our digital systems. This is a building blocks for our digital system. So next, we need to reduce our logic gates. However, it is very important. So we need to reduce our logic gates usage to make our circuit very simple and very effective. Okay. So for that, this technique plays a vital role to reduce our logic gates. We are having two techniques for reduce this logic gates usage. So in this one, so to simplify our Boolean expression or circuit, we need to use a fewer gates for simple connection without changing its function. We are not going to change any of the function, but with the help of few number of logic gates, we are all the operations which we needed. Okay, for cost and circuit complexity, and we also increase our speed and reliability, and we can also even save our power. Okay, so we are going to use a minimum number of logic gates to perform all the usages. Okay, so our next is, so we are having methods for logic gate reduction. In this, the first technique is Boolean algebra simplification. So here we are using the laws. Three laws. We are having laws, Boolean theorems. With the help of this Boolean algebra, we are going to simplify our logic gates. The major disadvantages is that it is very difficult for our complex circuits. Whenever the variable is increases, it becomes a very tough process. So next is visual representation. It is purely symbolic. We need to know the concept, how to minimize the Boolean expression. We need to know all the laws. If you forget that laws, all the process will be dropped. So this is a major disadvantage of this Boolean algebra simplification, and it is also limited to only 2 to 4 variables. Beyond that, we can't apply this manually. Okay, so the next is equivalent forms. We have many simplified forms which is make it harder to know which is optimal. Okay, so we need to use a trial and error method here. So the next is, it requires a strong algebraic knowledge. We need to know, we need to thorough this full Boolean laws and theorem, then only we can able to simplify effectively, or else the result will be error. Okay, so the next technique is K-map, Cornac map. So it is very easier method. Without knowing your laws and theorems, we can able to simplify our expression with the help of this K-map. So it is a graphical method which is used to simplify the Boolean expression easily and quickly. Okay, so it consists of some of the rules. We need to follow the rules strictly. So then only we can able to get your correct result. Okay, so it helps to find minimal SOP and POS forms. So it consists of two forms, which is SOP and POS form. SOP means it is a sum of product, and POS means it is a product of sum. Okay, so the K-map is completely work depends upon this SOP and POS forms. So first, SOP means it is a sum of products. Look at this example. I have notated function of A comma B comma C equal to A bar. Okay, so above A I have noted a dot line, right? So that is represent bar term. Okay, so bar A bar BC plus A B bar C plus A B C. So this is a sum of product terms. Okay, so this is in this each product term represents AND gate. Okay, so in between, note that we are having the OR gate operation. Okay, so to combine all these input variables, intermediate we are having sum, and in between your input variables we are having product, which is called sum of product. Okay, so and the next is product of sum. So here the expression is in the form of product of sum. So look at this example. So here the function is a comma b comma c equal to a plus b plus c bar, product of a bar plus b plus c, and product of a plus b bar plus c bar. Okay, so here in the intermediate we are using the product terms, and in between your input variables, note it is a sum, which is called product of sum. In the intermediate, we are using the product, and in between your input variables, we are having the OR operation, which denotes your product of sum. Okay, so and then this is some of the features of sum of product and product of sum. So in this, SOP means we know that it is a sum of product, POS means it is a product of sum. Okay, so while solving this K map, we represent number of ones in truth table while representing the sum of product. Okay, in representing POS, we are representing 0 in truth table. Okay, to notate our product of sum, we notate as 0. Okay, in canonical form, we call the sum of product as min term and also product of sum as max term. Okay, so the simplification will be done by grouping ones in K-map for SOP, and also the simplification can be done by grouping zeros in K-map for product of sum. Okay, so it consists of lots of procedure. So, but compared to your Boolean theorem, Boolean algebra, we are having more advantage using this K-map. We just know the procedure. If we know the procedure, mean we can able to solve very easily. But when coming to your Boolean algebra, we need to know all the laws and how to apply. We have to know. So if we change anything, the result will be in error. But coming to your K-map, it is a very, very easy method to solve or to reduce our Boolean expression. So if we reduce our Boolean expression, obviously we can reduce our logic gates. Okay, so the main advantage of this K-map is it will simplify our Boolean expressions easily, so which will reduce our complex logic expression into a simpler form, and number of gates also reduce, and it will provide a visual method. We can able to see how we are mapping. Okay, so and also it will reduce our human error because it follows a systematic approach. We need not to know the Boolean algebra laws theorems, right? So our next is optimized circuit design. So it will be very faster and cost effective for digital circuits, and it is suitable for manual simplification up to your 4 to 5 variable Boolean function. So up to 4 to 5 only it is very effective. After 5 variable, we will move towards a Quine-McCluskey method. Okay, so but normally compared to your Boolean algebra, the K-map has more advantages. We will use this K-map. Okay, so the next circuit is combinational circuit. So the digital system completely works on our logic gates. So that is a building blocks. So with the help of logic gates, we are going to build our combinational circuits. So look at this. A circuit is a digital circuit input variables not on past inputs, which means it will be only depends upon the input which we are passing, right? For example, if we take the logic gates, in the logic gates, whatever if I'm passing as input, the output will be depends upon your inputs. Okay, so not upon what we have stored. There is a no storage available in logic gates, right? So it is completely depends upon a number of inputs, the output will be produced. So that is our combinational circuit. It does not contain any storage. Okay, so a combinational circuit is a digital circuit in which the output will be depends on our present input variables, not on past inputs. Here this not on past input denotes there will not be any storage involved. Okay, so it performs an arithmetic and logical operation using our logic gates. So we are having some characteristics of this combinational circuits, which is it doesn't contain any memory. So the output will be depends upon only your inputs. There is no feedback path also. It is normally implemented with the help of our logic gates, and it is represented using truth table or Boolean expressions. So next is, so some of the basic combinational circuits are adder. Adder, which we know that it will perform your addition operation, and next is subtractor, which will performs our subtraction operation, and next is multiplexer. So multiplexer means we call it as many to one form. Here we are having the more number of inputs and only one output. So like this, demultiplexer, encoder, decoder, comparator. These are the some basic combinational circuits we have in digital. So next is adders. So in the adder, we are having certain rules in digital, right? So the binary addition rules are, so look at this rule explanation. 0 plus 0 is 0, and 0 plus 1 means 1. 1 plus 0 means 1. 1 plus 1 means 0, 1, which is sum is 0, carry will be 1. And next combination is 1 plus 1 plus 1 means the sum is 1, carry is 1. This is a rule to perform our addition operation in our digital. So normally we are having the types of adders like half adder, full adder. Okay, so this is a basic adder which is very essential for all types of circuits. So in the first one we are having half adder. Half adder means it will add 2 bits. Okay, so and then full adder it will add the 3 bits. So normally while performing or addition operation, we will have sum and carry as output, right? So in the half adder we are adding the 2 inputs and it will produce the output as sum and carry. Okay, so while applying or design rules, we will get the sum expression as A XOR of B, carry expression as A into B. So in the full adder, it will add the 3 bits, which is A, B, and carry in. So while simplifying this with the help of K-map, we will get the sum equal to A XOR of B XOR of C in. C in represents carry in. So carry will be AB plus BC in plus AC in. Okay, so and the next is subtraction in digital systems. Addition is normally like how we are doing. So here we need to consider only 2 rules. So when 1 plus 1 means 1, 0, which is sum is 0, carry will be 1. 1 plus 1 plus 1 means sum will be 1, carry will be 1. This is a rule to perform the addition in digital system. So coming to your subtraction, so it is performed with the help of complement form. We will not directly doing the subtraction what we are normally using method, right? So here in the digital, we are using the complement form. Okay, so in this complement form, we are having 2 complement method. First is 1s complement and second one is 2s complement, right? So 1s complement means nothing. So if we are having 0 means we will invert that bit as 1. For example, 1, 0, 0, 0 means if I'm taking this complement form means your answer will be 0, 1, 1, 1. I'm going to convert your 0 to 1 and 1 to 0, which is called 1s complement method. And second one is 2s complement method. Okay, so after applying this 1s complement, I'm going to add 1 along with this answer. Okay, for example, if I'm taking the 1, 0, for example, 0, 0, 0, 0, if I'm going to take it as bit, so if I'm going to perform the 2s complement means first I need to perform the 1s complement. Okay, I have taken the example 0, 0, 0, 0. Okay, now I'm going to perform the 1s complement. 1s complement means 1, 1, 1, 1. Okay, so to perform your 2s complement along with your 1, 1, 1, I need to add 1 along with your answer. Okay, so now 1, 1 means we already see the addition rules. 1, 1 means your sum will be 0 and carry will be 1. The remaining procedure will be same as your addition process. Okay, so in this digital system, we will perform the subtraction with the help of using your complement methods only. So either I can use a 1s complement method or 2s complement method. Okay, so for example, here I have mentioned subtraction operation of your digital system. Look at this. I have taken an example. A equal to 1, 0, 0, 0. B equal to 0, 1, 0, 1. The decimal representation of first binary input is 8 and 3. Okay, so normally if I subtract 8 minus 3, we will get the answer as 5. Okay, so in this we have used the digital subtraction. So first I need to take the 1s complement of b, because here we have notated the a minus b. This minus b will be carried out with the help of complement method. Okay, so 0 1 0 1, if I'm taking the 1s complement, means it will be 1 0 1 0. Okay, so this is 1s complement. To perform the 2s complement, I need to add 1 along with this 1s complement. Okay, now I will get 1 and then carry, it will be given to a further. Okay, so 1 0 1 0 means, so we will get the answer as 1 1 0 1. Okay, so after that, so normal addition, so 0 plus 1 means 1, 0 plus 0 means 0, 0 plus 1 means 1, 1 plus 1 means the sum will be 0, carry will be 1. So in this way the subtraction will be performed in our digital system. So this is your half adder circuit. Okay, so in this half adder we are having the 2 inputs and 2 outputs. So 2 inputs, here it is a and b, and sum and carry as output. Okay, look at this truth table. So we are having the 2 inputs, so the combination is 0 0 0 1 1 0 1 1. Okay, so we have the rules, right? So in addition, if we are having 1 plus 1 means the sum will be 0, carry will be 1. 1 plus 1 means sum will be 1 and carry will be 1. Okay, so now I'm going to add 0 plus 0 means, so both 0 means we are having sum as 0, carry as 0. 0 plus 1 means sum is 1, carry is 0. 1 plus 0 means sum is 1, carry is 0. 1 plus 1 means we will have the sum as 0, carry as 1. Okay, so this already I have explained. So in this sum, you see this 0110 is a output of your XOR gate. Okay, so for that only we have represented the sum in XOR gate, and carry is the representation of AND gate. So for that only we are using the AND gate. For this, notate your carry representation in your logic diagram. So this is your half adder, and some application of this full adder and half adder is a ripple carry adder. Okay, so here I have taken a 4-bit full adder. Okay, so the full adder normally it will add a 3 inputs, which is A, B and C. So and it will produce the output as sum and carry. Okay, so these are the 2 outputs and we are having the inputs A, B, C. Okay, so first, in the first block, it will take the inputs and it will produce the output sum and carry. And carry will be propagated to the next blocks, which is called ripple carry adder. Okay, so each block will take considered as 3 inputs. In the first block, we are having the inputs A, B, C. Okay, so it will take the inputs and it will produce the sum and carry. Okay, so the next block will wait up to the input carry get it into that block. Okay, so after getting that input carry only, the next block will be start to process. Okay, likewise this will goes on up to your 4th block, which is called ripple carry adder. Here the carry is rippled to your next blocks. Okay, so in this case we are having the disadvantage, it is very slow operation. Why? Because so upcoming blocks have to wait for the incoming carry. After getting this incoming carry only, it will propagate the output. Okay, so it will take some amount of time, we call it as delay. Okay, so which is called it as propagation delay. So it will be, if your delay is more means your speed will be reduced. Okay, so your speed will be reduced, mean obviously it is a slow operation. Okay, so here the propagation delay, it will be increases with the number of bits. Okay, it is not suitable for high speed circuit. Why? Because here the propagation delay will be more. Okay, I cannot apply this for your high speed circuit. Okay, so and power consumption also more. If your delay is increased, definitely your power consumption is also more, and obviously your operation will be slowed down. So this is the major disadvantage of your ripple carry adder. Okay, so we overcome this ripple carry adder disadvantage using your carry look ahead adder. Okay, so here we need to wait for your carries. That is a major disadvantage. Okay, so for this waiting time will slow down your operation, right? So to overcome this only, we are moving towards your carry look ahead adder. So in this concept, we introduces our carry generation and propagation logic to compute in parallel manner. Okay, we will have some formula basics to use this carry look ahead adder. We will not wait for any result at any instant. It will produce a output depends upon our carry generation and propagation logic. So it will eliminate or ripple delay by predicting the carry outputs faster. So here it will perform as high speed because it will not wait for any input carry. Okay, so the delay is very less compared to our ripple carry adder. So obviously it will be operating high speed. Okay, so these are the some of the high speed adders we are using in digital systems. That is carry skip adder. Okay, so in this carry skip adder, we will add the bypass certain stages, so it will not affect your next bits. If carry is does not occur, means it will not affect the next bits. Okay, so which will reduce our propagation delay for group of bits. Okay, so next is carry select adder. So in this carry select adder, so we will calculate by keeping carry in as 0 and also carry in as 1 simultaneously. Whenever your input is paused, so depends upon your input, it will take the result from your carry in 0 and carry in 1. Okay, so this is very faster, but complexity is very somewhat moderate. So next is carry save adder. So it is common in multipliers, which will avoid carry propagation between your adders. So here these three adders are called as high speed adders. Okay, so by using our advanced adder architecture like carry look ahead adder, carry save adder, carry select adder, our delay and speed limitations will be effectively overcome. So we are having some of propagation delays in our triple carry adder and carry look ahead adder that will be overcome with the help of this high speed adders, which is carry skip adder, carry select adder, and carry save adder. So this is some basics of our combinational circuit. Our next circuit is sequential circuit. So as I said, in the combinational circuit, we don't have memory concept. Coming to your sequential circuit, so it consists of a combinational circuit. Along with your combinational circuit, there is a memory element, which is called sequential circuit. Okay, so in the sequential circuit, we are having that combinational circuit. Along with that, we are having memory elements. We call it as memory elements, which is combined to form sequential circuit. Okay, it is also a type of digital circuit which output depends upon both present input and past input. So in the combinational circuit, that is a only that output will be depends upon only your present input. Okay, in this sequential circuit, that output will be depends upon your both present input and past inputs. Okay, so here it in the sequential circuit, it uses memory elements to store or past information. Okay, so next our key components or combinational circuit. So in the combinational circuit, we have seen whatever I'm applying as input, so that will be given for you. The input combination will be processed and depends upon the input combination, the output will be given, right? So and the next one is memory elements. In the memory elements, we will use a flip-flops and latches as storage elements. So this is a very important topic on in your sequential circuit, flip-flops and latches. With the help of this flip-flops and latches only, we will build our memory circuits. Okay, so it will store the state information, either it will be a 0 or 1. Okay, next is clock signal. It will synchronize your operation. So these are the very key components of your sequential circuit. It consists of combinational circuit, memory elements, and clock signals. And we are having the types of sequential circuits, which is synchronous and asynchronous, right? So synchronous means all the elements, memory elements, are triggered by a common clock signal. Okay, and next is asynchronous. So asynchronous means, so here we have without a common clock, we are giving a independent changes. Okay, so synchronous means it is triggered by a common clock signal. Asynchronous means it is not by a common clock. Okay, for example, if it considered 3 blocks, means first block will get a clock signal and second block will get the output of first signal as a clock for your second block. Okay, so if the third block means the third block will get your clock signal from your second block, which is the output. So the output will be given to the third block's inputs. So that is a major difference between your synchronous and asynchronous circuit. Okay, synchronous is nothing, it will use your common clock signal. Asynchronous means it will not works on common clock. Okay, so this is a types of sequential circuits, some of the examples of sequential circuits. So in the flip-flops, we are having the 4 types of flip-flops: SR flip-flop, JK flip-flop, data flip-flop, and delay flip-flop, toggle flip-flop. So we are having counters, shift registers will shift your input bits, and sequence detectors. So in this sequential circuit, we are having some of advantage. We can store the information compared to your combinational circuit. We can store the information. It is suitable for our timing and control applications, which is used in computers or processor and communication systems. So that's all. So this is our basics, some of the basics of our digital systems. So we have seen the number systems and then combinational circuit and sequential circuit. Okay, thank you.
Yeah, thank you so much for your presentation, ma'am, and for our
Yeah, okay,
participant.
ma'am.
Yeah, and for our participant, if you have any question for the speaker, please add them to the chat or you can raise your hand.
Yeah, okay, ma'am.
Oh yeah, for first question, we have question. Could you please explain how digital system have transformed modern industry like communication and automation? The question from Miss Hori. Thank you. Hello?
Yes, you have asked the question. Could you please explain how digital systems has transformed modern industries like communication and automation, right? So here they are using the building blocks of your digital systems, which is a combination of combinational circuit and sequential circuit. So it consists of FPGA kits, and likewise we are having the so many techniques of digital system. It will be built in a circuit, so that will be used for your communication and automation process. So we are using this digital systems for foundation of our modern organization. So it will uses for automation, information sharing, and data driven.
Okay, thank you. And then the second question, could you give an example of how digital systems are applied in everyday life without us even realize it? The question from
Yes,
Miss
in the
Zahra.
yeah, in the everyday life, we are using the mobile phones, which uses a digital concept, right? So normally we are having the mobile phones in our hands, right? So this is a very common example for your digital system.
Okay, thank you. And then the last question, what are some current trend or innovation shaping the future of digital system today? The question from Mr. Zainal.
So real-time data access and resources optimization, process standardization, and reporting and analytics, we are using your or shaping the future. So we are using this as integration of rules. So for example, a company like Toyota, which uses a ERP system to integrate our production, supply chain, and finance. So this allows real-time monitoring of inventory, efficient scheduling of manufacturing, and accurate financial forecasting. Yeah, okay.
Thank you for your answer. I guess no one else asking again, ma'am. Yeah, and before I close this event, for all participants, please open your camera. I will take a picture on the count of three for documentation. Okay, 1, 2, 3. Okay, another one. 1, 2, 3. Thank you for your kind cooperation. Finally, we come to the end of this setting lecture today. We would like to thank you for Miss Nafeeza for the wonderful information and
Yeah,
sharing
thank
your
you, ma'am.
knowledge. Yeah, thank you so much,
Thank you. Thank you
ma'am,
so much.
and have a nice day.
Thank you. Have a nice day.